The section for this video is going to be working with simplifying rational expressions. So we're going to start with identifying them, work with some domain and other properties that show up with those, and then bring it all together with simplifying rational expressions and some examples that go along with those. So starting off with identifying rational expressions. What's our definition of these things? So our definition, you'll see here, a rational function is written as a ratio of two polynomials. So it's a really fancy way of showing what we have written algebraically here, which is a fraction with a polynomial in the numerator spot and a polynomial in the denominator spot. One up top, one down below. Now we do have some other properties showing up in here with the rest of our definition stating where p of q, our denominator in this example, is not equal to 0. We're going to get to the specifics regarding this later on in our domain section, but starting off with what we have currently, this is our definition. But again, I want to make sure it's very clear that we're highlighting and zeroing in on the part that's saying it's a ratio of two polynomials. So polynomial on top, polynomial down below. Some examples of non-polynomials that are showing up or can show up with some of these are the absolute value sign, roots and radicals, so the square root, cube root, fifth root, things like that, and trigonometric functions or trigonometries, things like sine, cosine, tangent, cotangent, cosecant, and secant as well. If you're unaware of what those are, that's fine. They're not necessary for this section. All we're using those for, and we're just noting this, is just to say these are examples of non-polynomial functions. So our definition says the top is a polynomial function, bottom is a polynomial function, then cool, we have a rational expression and we can work with this. So let's take a look at our first few examples that we have here. We're asked, is the following a rational function? So looking at our first thing that we have here. I'm looking at the numerator, looks like that's just a binomial. Looking at the denominator, that's also just a binomial. I have no absolute value signs, I have no radicals, and I have no trig functions. So looking at number 1, yes, this thing is a rational function. Let's take a look at B. We're given h of x is equal to the square root of x divided by 7. Well, look at the denominator and I say, well, this thing actually is a polynomial. It's just written in a non-conventional way. We're used to seeing it written with x's and other terms written in there, but we can have a one-term polynomial, a monomial in that instance. I look at the numerator and I notice, well, I have a square root of x. That's a root or a radical that we have there. So because the numerator isn't a polynomial, then that means the entire thing is not a polynomial. And therefore, or the entire thing isn't a polynomial, the entire numerator isn't a polynomial, therefore the entire function is not a rational function. Yeah, so we see here it contains a radical somewhere, so it can't have that. Looking at C, saying 2x squared minus 2x minus, it should be this 1 should be right here. And we might look at this and say, well, hold on, I don't have any denominator. And our definition has something in the numerator divided by something in the denominator. And both of those somethings are polynomials. Well, remember back to our rules from previous sections and previous discussions. Anything that is not explicitly written as a fraction is always assumed to then have a denominator of 0. Or sorry, not a denominator of 0, a denominator of 1. So looking at this thing, this is actually 2x squared minus 2x minus 1 all over 1. And 1 is a rational function, so therefore, in its entirety, this 1 is a polynomial, therefore meaning this entire function is indeed a rational function. And looking at D, we have f of x is equal to 5 divided by x here. Again, the numerator, it's a monomial, only has one term. The denominator is a monomial, it only has one term. There's no absolute value signs, there's no roots or radicals, there's no trigonometry, so therefore this thing is also a rational function. There we go. So if you are asked or you're looking at something and wondering, is this thing a rational function? Come back to our definitions that we have here. You can also come back to, and I would think it's a very good idea to reference or maybe put a note of the examples of non-polynomial functions. I'm going to put a little star by that. I think that's a good thing to keep in mind as we're going through these. So this would be how we'd go through and identify rational functions. The next part of this section that we're going to cover is the domain and identifying vertical asymptotes of rational functions. So our main definition that we have here with this, or the thing we need to look for the domain, and note, is that the domain of a rational function is everywhere except for values that make the denominator 0. And we are specifically looking at the denominator here with this. So that's our main focus with a lot of these, if we're told to find the domain or if we are told to find the vertical asymptotes of something. So the reason we can't have that is because we can't have, and we would end up creating, division by 0 if we have our denominator equal to 0. When that happens, we have a few things that show up with this. First and foremost, from a strictly numerical standpoint, we do not know what the actual answer is. We don't know what something divided by 0 is as a one specific number answer. It simply doesn't exist, or we can't calculate it. Another way you can think on it too. The other one that we can look at with this is it creates what are referred to as vertical asymptotes on a graph. And we'll take a look at those later on to see a visual of what these look like. But the specific name of those is referred to as vertical asymptotes. Now the main way we're going to go through and actually identify what the domain is or identify what the vertical asymptote is of a rational function is using our second bullet point here. And we can calculate that by setting the denominator specifically equal to 0. I'm going to underline that permanently with that. Denominator equal to 0. And then we are going to solve the resulting equation that we make. Based on what we have learned so far, I think it's a very valuable hint to say, start with using our any and all factoring techniques that we have. We will learn other techniques to solve different types of polynomials later on in the course, but for now, we're going to start with using factoring. So we are told to find the domain or find the vertical asymptotes. We set the denominator equal to 0, and then we start actually solving that thing. Now, when we actually find the domain, there's a few ways you can write this out here. We can write this using the double R that we saw show up in our previous sections relating to functions. And then we're going to list the specific number or numbers that we cannot use. And this whole statement right here is the same as saying the domain is all real numbers except for, and then the numbers that we have listed here are the specific domain restrictions or numbers that we can't use. Now you are not required to write it this way for my class, but you may see it written in this manner in textbooks or in other classes or things like that. The way that I would recommend writing this out for yourself, which I think is a much more straightforward way and a bit more intuitive, is to simply write out for yourself x is not equal to, and then we will list the number or numbers off, just separating them out with commas. So we will take a look at the 4 examples written down here to see how we go through and determine the domain of each of these functions, noting that we are going to leave our answers as fully reduced fractions. So here we have our first example. We're looking at f of x is equal to 1 over x plus 3. Now we're told to define and determine what the domain of this function is going to be. So our process for doing that is specifically and only working with setting the denominator equal to 0 and then solving for x values from there. So we're going to start with doing that. So we're just going to write that out for ourselves. So the denominator, x plus 3, equals 0. And now we're just going to be solving for x. So we were doing that. We are going to subtract 3 from both sides. We are getting x is equal to negative 3. Now we just identified which x value or values, when plugged into the denominator, create division by 0. So we have to note to ourselves off to the side that we are finding the domain. So I'm going to write out for myself domain. And again, two ways you can write this out for yourself. You can do this double R, that there, or, and this is the way that I think is particularly useful and kind of more straightforward way of listing it, x cannot equal -3. So for your final answer, you could list it as this method here, or this form here, that works fine, or you can use the second one here. Both are perfectly acceptable. I just wanted to note what each of those would look like in an example. But for the purposes of our class and most classes that you're going to be working with, this second one that we have down here, this x is not equal to -3, this is probably the easier one to remember and work with. So I'd recommend writing that out for a lot of these answers as you're getting them. I am going to be using that in our second, third, and fourth examples here shortly as well. So here we have example 2. It's getting a little bit more complex. There's a little bit more going on in the numerator, a little bit more going on in the denominator. Again, I'm looking for the domain, which means all I'm looking for is where is the denominator equal to 0. So just like we did with example 1, I'm going to rewrite this to be just where the denominator is equal to 0. And that's all I'm going to solve for. And using our techniques that we learned in chapter 7 to factor this thing out, I'm looking at this and seeing, okay, I need to find two numbers that multiply to give me -3 and add together to give me -2. And then I can just write this thing into its fully factored form. So this would be 7.2 material. It turns out our two numbers are going to be a +1 and -3. You can write these in reverse order, that's perfectly fine, as long as one is x minus 3, the other is x plus 1. Now that we have this thing factored, again, I am solving for where this is equal to 0, so I need to split this thing up into two parts, and I'm going to solve where each of these things are going to be equal to 0. We just need one equaling 0, and that will make the other one equal 0 as well. So looking at our first one, we have x plus 1 equals 0. I'm subtracting 1 from both sides. And I'm getting x is equal, oops, glitchy in there, x is equal to -1. And for the other one, I'm going to be adding 3 to both sides. Once I do that, I'm getting x is equal to 3. So now, writing this out as our final answer, I'm getting the domain is x cannot equal -1 and 3, or two values that we found there. Make sure when you are writing these out for yourselves, you're making it clear that this is two numbers. I've seen plenty of people forget to put that little comma right in between there, and they'll write an answer or type an answer as -13, which anyone who doesn't see the comma is going to interpret that as -13, and you might get dinged for that. So just make sure you're listing all those values separated with a little bit of a comma in there, and then you're good to go. So there we have example 2. Looking at example 3, we're going to follow along the exact same way, but pretty much the exact same pattern that we did with our first two. I'm trying to find the domain, so I need to set the denominator equal to 0. So I'm writing out the entire denominator, saying equal to 0. Now I'm noticing I have all of this raised to the second power. So I can expand this out for myself and write it as x plus 1 times x plus 1 equals 0. And now, just like I had with example 2, I have two things multiplying together. Turns out that they're the exact same thing, so I just need to solve one of these, and it's the answer for both of them. And then I'll have my final answer. That'll tell me where I'm going to make the denominator 0, and then we'll be good to go. So I'm subtracting 1 from both sides. I'm getting x is equal to -1. So off to the side, then we're writing out for ourselves our domain. Writing that domain is that x cannot equal -1. It can be anything other than -1. We're good to go. So there we go, example 3. And our last example with the domain vertical asymptotes, f of x is equal to 1 over x squared minus 1. So just like all of our previous examples up to now, I'm trying to find where is the denominator equal to 0. So I'm going to start off with writing it out as the denominator equaling 0. Looking at this and I'm noticing, well, I have a perfect square here, I have a perfect square here. So now I can factor this thing out. It's a difference of squares. I'm getting x plus 1, x minus 1 is equal to 0. And just like we did previously, now I can split this thing apart. I'm getting x plus 1 equals 0. I'm getting x minus 1 equals 0. And I can solve each of these individually. So for our first one, we're subtracting 1 on both sides. Getting x is equal to -1. With the other one, we're adding 1 to both sides. We're getting x is equal, x is equal to +1. So again, bring it all together. We're listing out our final answer for our domain. That x cannot equal -1 and +1. Gotten the question from time to time. I just want to make a quick note of this here. It shouldn't matter which order you list your final answers. Some people prefer the negative first, some people prefer the positive first. As long as you have them all listed out, separated with the commas, you should be good to go there. But those are our 4 examples for finding the domain of rational functions. To get an idea of what the visuals of these vertical asymptotes look like, we've come over to Desmos.com. It's a free website you can use to enter in equations and see what these things look like graphically. So we're going to use that and take a look at our 4 different examples that we have here and see what they look like graphically, so we can see what these vertical asymptotes actually look like. So let's take a look at example 1 that we had here. So here's what the standard graph looks like. It's got a fairly unique shape and design to it we have here. And we're noticing here, because again we're looking for vertical asymptotes, we're noticing that this thing looks like the graph gets closer and closer and closer along the x values to this -3 that we have right here. So I'm going to put in another vertical line here just to show that line there. Now if we notice, if we move up on this red line, which is the actual graph, gets closer and closer and closer to an x value of -3 from the right side, and same thing from the left side, it's getting closer and closer and closer to -3, but it never actually reaches there. So this is again because we cannot have any division by 0 showing up. We get these vertical asymptotes or areas where we cannot have any actual output value showing up with it. And this is what it ends up looking like graphically. Get areas showing up that we just can't cross. So let's take a look at our second example. We're noticing, if you remember in example 2, we had 2 different asymptotes that were showing up. We had one at -1, so somewhere right along here. Turn that one on. So you see that showing up. And we calculated our other asymptote at x equals +3. So we'll adjust this a little bit. Make that a +3. Let's bring that one up. There we go. And we're seeing that in both of these instances, graphs are getting closer and closer to those asymptotes, but again, never actually crossing them. So no matter which direction we're coming from, we never actually cross or get equal to those x values. So that's what these asymptotes end up representing on the graphical level for these first 2 examples. Our third one we have here, we had an x-intercept at x equals -1. So leave this one on. And we see that, again, it's Bit of a unique one, a little bit different in how it's set up. But similarly to the other ones, I can never have an x value of -1 plugged into this thing. It just turns out in this example that we get closer and closer and closer to this thing, but again, never actually reach that x value of -1. And then our last example that we had, which was number 4, we had asymptotes at x equals +1 and x equals -1. So we'll get those in there. And yet again, we're seeing instances where the graph gets really, really close to these asymptotes, but it never actually reaches them or crosses over them. So that's what these asymptotes and the domain restrictions look like on a graphical level with all 4 of these example equations here. So as a quick summary, what we did with our domain and identifying the vertical asymptotes, again, we were looking to see any and all x values that would create division by 0 in the denominator spot. Our method for doing that was going through and saying the denominator equal to 0 in each of the equations, and then solving it with whatever means necessary that we have at our disposal. In this case, we used a lot of factoring. We had our 3, or I guess I should say our 4 examples, and our answer showing up here. There is a typo from number 2. This should actually end up being 3, -3, 1. So small typo there. But otherwise, this is our process and summary and everything that we have for going through and using the domain and range with rational expressions. The last part we're going to cover with this section is reducing rational expressions down. This is probably the most important section or part of this section that we are going to cover, primarily because this is something that we're going to be using throughout all of Chapter 8 moving forward. So the main thing that we are looking for is, going back to our core definitions with fractions, is to make sure that everything is fully reduced. And remember, by our definition, with a regular fraction, it still applies here, a rational expression is considered to be in lowest terms when the numerator and denominator only have a common factor of 1, meaning there's nothing I can factor and divide with the numerator and the denominator. So if we look at a quick general example of this, if we have a, b, and c as polynomials, and b and c in this instance are polynomials that do not equal 0, then if we have a starting expression here, where we have the polynomial a times the polynomial c in the numerator spot, the polynomial b times the polynomial c in the denominator spot, and we look to reduce these things down, we notice, well, both of these have a c in the numerator and the denominator spot. So those can cancel out, and what's left over? Just the polynomial a and just the polynomial b. We have that thing fully reduced then. That's our general idea of what we're going for with these, but we have our main process that we're going to want right in here. So I would recommend taking a second, write these things down for yourself. Pause the video if necessary to do so. If we're diving into our process, our first step, and this is again before we look to do any kind of canceling or dividing or any of that, we want to make sure we fully factor the numerator and the denominator before doing literally anything else. Really want to emphasize that there are a lot of people, when they read through this, they decide, I'm just going to start canceling things at random. There's an x up top, there's an x somewhere down below. I'm going to pick and choose and cancel those things out. We can't do that. We have to fully factor everything beforehand. Once numerator and denominator are both fully factored, then and only then can we actually divide and cancel out something from the numerator and the denominator spot. We have to make sure we're choosing common factors, meaning two things that are the exact same as one another. So if I have something such as x plus 1 in the numerator spot and x minus 1 in the denominator spot, I cannot cancel those things because they are not common factors. They are not the exact same as one another. Now, in some instances, depending on the numbers that we've been given, you may also need to factor out a -1 if only signs need to change in some of these numbers and functions that you're working with. This is not the most common of occurrences, but it does show up just frequently enough that I do want to make a note of that for you as something to keep an eye out for as you're going through these problems. Now, it should be noted with this entire section that we have here, and really this entire chapter, factoring is going to be extremely important as we go through all of this. So if you need to, go back and take a look at the Chapter 7 notes and Chapter 7 videos that have been posted, because we're going to use factoring for all of these problems. We'll see here shortly. We'll get started on looking at the 4 examples that we have listed right down here. So here we have example 1 of simplifying rational functions down. So we're starting with x minus 1 over x squared minus 1. Now, as our process is telling us, we want to fully factor the numerator and the denominator before we do anything else. So looking at the numerator, I can't factor that any further, so it's just going to stay as x minus 1. The denominator is a difference of squares, which means this can be fully factored into x minus 1 and x plus 1. I can't factor the denominator any further, so we're good to go on step 1 of our overall process. Step 2 tells us that we need to divide and cancel out any common factors both the numerator and the denominator have in our resulting function. So we're noticing here that we have an x minus 1 in the numerator and an x minus 1 in the denominator spot. Because those are the exact same, I can therefore cancel those entire things out. Now when I'm canceling those out, it doesn't mean that they are both becoming 0 and they're gone. Remember that anything divided by itself is the same as saying 1. So each of these becoming just a single 1 in their respective places. And my new resulting rational function is going to be 1 over x plus 1. This portion down below here, this new thing that became 1 is multiplying with x plus 1. And 1 times anything is just whatever we started with. So therefore, we have our final answer for the first example. It's a fully reduced fraction of 1 over x plus 1. Here we have example 2, where we have 8n minus 96 being divided by 3n minus 36. Following the same process that we were given previously, we are again looking to fully factor everything in the numerator and everything in the denominator spot before we do anything else. Looking at the numerator, I'm checking to see, is there a greatest common factor between both of those terms? Yes, there is. So I can factor out an 8 from both of those. I have n minus 12 left over. If I look at the denominator, both of those terms have a common factor of 3. So I can factor a 3 out and have an n minus 12 left over. Now I'm looking at both the numerator and the denominator, noticing I can't factor anything else out from each of them individually, so both of those are fully factored. Now I can go and divide and cancel things out. And in this step, I'm noticing both the numerator and the denominator have an n minus 12 in them, meaning I can cancel an n minus 12 and an n minus 12. Those would each become 1. And then 1 times 8, 1 times 3, gives me a result of 8 over 3. I can't reduce that down any further. Therefore, my final answer as 8 over 3. Example 3 gives us something a little bit weirder than what we've seen previously, in that we have a monomial in the numerator and in the denominator spot. And we have multiple variables showing up in both the numerator and the denominator spots. But we're still going to follow our process, and that's going to get us right to our final answer. So I'm looking to the numerator and seeing, is there anything I can factor out of the numerator? And no, there isn't. We can never factor anything out of just a monomial, which means the denominator can't have anything factored out of it either. So both of these things are fully factored as best they could possibly be. So now I'm looking to see, can I cancel anything out with the numerator from the numerator and the denominator spot? So I'm going to look at this as numbers, then looking at x's, and then looking at y's. So piece by piece with this. So looking at my numbers, I have a 15 in the numerator spot, a 3 in the denominator spot. Both of those can be divided by 3's, which means that the 15 is going to become a 5, the 3 is going to become a 1. So my new fraction is now 5xy over x cubed y cubed. Move this equal sign down just to make it look a little bit nicer. There we go. And let's make a better 5. Oops. Come on. Things glitching on me a little bit. There it goes. Now we're good. So now I'm looking at 5xy over x cubed y cubed. And I'm looking at the x's. I have an x up top, and I have an x cubed down below, so I can cancel one of the x's up top with one of the x's down below, which means I'm now going to have a new numerator of 5y over x squared y cubed. This was using our properties of exponents to reduce that down, again discussed in previous videos and previous chapters. And then lastly, I'm looking at my y over y cubed. I can cancel one y up top with one y down below, giving me a y squared left over in the denominator spot. And this gives me 5 over x squared y squared. I now don't have anything else that I can cancel from the numerator and the denominator spot, so I have my final fully reduced answer. And last but certainly not least, we're going to take a look at example 4. So looking at this one, yeah, there's a lot of stuff that I can do to factor out the numerator and factor out the denominator. So what I'm going to do with this is I'm going to come off the side here, and I'm going to factor each of these things individually, just so I'm not losing track of what I'm doing overall with the whole problem. So if I'm going to factor the numerator, just start with that. Again, first and foremost, I'm looking to see, do I have a greatest common factor amongst all of these terms? And I do. It's going to be 3. So what's left over? I have x squared plus 6x plus 8. And now from here, I'm looking to see, can I factor anything here? And I can. This can be broken down using the material that we learned from 7.2 into x plus 2 and x plus 4. And now I can't factor that out any further, so I'm good to go there with the numerator. Right next to it, let's go ahead and factor the denominator out. So our denominator is 3x squared minus 48 to start. Again, I'm looking to see, is there a greatest common factor? And there is. It's also a 3. And left over, I have x squared minus 16. Again, I'm looking to see, can I factor this x squared minus 16? This is a difference of squares, so I can factor that. And that's going to become x minus 4 times x plus 4. So I've fully factored the numerator, I've fully factored the denominator. Let's bring both of those right back into our main work area here and start canceling some things out. So I have 3, oops. I have 3x plus 2 and x plus 4 all over 3x minus 4, x plus 2, or x plus 4, I should say. There we go. And now with everything fully factored out, now I can look to cancel things. I'm noticing that I have a 3 that I can cancel from the numerator and the denominator spot. And I also have an x plus 4 that I can cancel from the numerator and the denominator spot. So all of those are becoming 1s. And then after that, I'm looking at what's left over. Well, I have an x plus 2 in the numerator spot. I have an x minus 4 in the denominator spot. And I really can't cancel anything else out because there's nothing I can factor first. So from here, can't do any more work. And I have my final answer, for example 4, of x plus 2 over x minus 4. So bringing us back to our overall process of reducing rational expressions, remember that the first thing that we need to do in our process is fully factor the numerator and the denominator before we do anything else. Only then can we divide or cancel out something from the numerator and the denominator to get to our final answer. And if you need to take 2 or 3 or 4 lines to cancel things out, like we did with example 3, or a little bit with example 4, to write everything out in its fully factored form, there's absolutely nothing wrong with that. Take all the time and lines of work that you need to make that happen. So we'll go ahead and reveal our final answers here, which were the same as what we got when we worked through them. I'll scroll down here and give you some extra practice problems if you would like to work on those. Again, I recommend pausing the video here to see, give yourself some time to work through these examples. Then I'll scroll down to the answers for these here shortly. Scrolling down to our final answers we have with these, we're getting to here. So this concludes everything that we have for section 8.1, simplifying rational expressions.